Good morning, everyone. Our next speaker is Professor Ward Wheeler. In his career, Professor Wheeler has developed theory and algorithms to interpret evolutionary patterns from multiple sources of phylogenetic information, including anatomy, behavior, and genomics. Professor Wheeler's talk title is titled Phylogenetic Supergraphs. So, Professor Wheeler, you may start whenever you are ready.
I'm trying to share my screen. There we go. And there we go. Say so if there's a problem. Good morning, everyone, and thanks for inviting me to this meeting. As was just said, I'm going to talk about graphs, supergraphs, and phylogenetic networks. So the basic organization of the talk is going to be, well, why we would want to do this, some definitions for the different objects we're going to talk about, common steps in these methods, and then two different basic approaches, one that emphasizes vertex or internal node HTU-based methods, and those that are based on edges or branches of the input trees, graphs, or whatever they are. Then I'll talk a little about the time complexity to get an idea of how much time this will take, and then a couple of empirical examples, and then what the general utility or why we might want to use such methods in analyses. Now, traditionally, consensus techniques have been used to identify common and disparate information among trees producing other trees. And there are lots of these techniques. So you have the strict consensus of Shu and Palamas, which presented common groups in all trees, which was great in the sense that you knew everything was there, but could rapidly fall apart to a bush if there was slight disagreements, even in only one of the inputs. Atoms, the atoms 2 actually is what everyone uses, not the atoms 1, but this is based on the intersection notions of all trees. Atoms 1 is not used because you could promote internal nodes to leaves. The Nelson consensus, which has been called different things and is somewhat ill-defined, but there are multiple techniques with elements of strict, majority, and semi-strict consensus in there. Then Margush and McMorris, the majority rule consensus, which puts groups present in majority of trees, which is used a great deal in summarizing input tree results, different sorts of methods. And then the semi-strict put forward by Bremer, which is based on some of the concepts of Nelson, which had consistent components present in all trees. So the idea of an unresolved component and a resolved component don't disagree, and the resolved component is presented. Now, the motivation of this talk is to expand this. And so there are some other consensus techniques that result in reduced trees or non-trees. So these are different than the previous ones. And the first would be minimally pruned trees, where one would delete taxa until a stable tree found. You lose taxa analysis, the results are not necessarily unique, and it's an NP-hard problem. This technique has been sort of rediscovered and republished many, many times. Maximum agreement forests from Hein et al. 96. So removing components until a stable forest is found. This is also NP-hard, and this is a technique that has not been used in empirical studies very much that I've seen. Now, supertree techniques are a component of this. They're sort of a generalization in that supertree techniques allow different taxon or leaf complements to be reconciled or made in consensus. They're graph-based methods in general, and they generalize consensus methods to allow for this different leaf complement. So one example of this would be the Gordon strict consensus as seen below, super trees. In this analysis, you can see that you have two inputs here. E is on the left tree, isn't on the right tree, but you can still have it in the consensus below. Now, the previous things we talked about all output trees, basically. Or forests in the case of minimally pruned in some cases, but there was no reticulation in the outputs. And now other methods actually can produce networks in the sense of having reticulate or in degree greater than 1 internal vertices. And these include consensus cluster networks, cluster split networks, cluster union networks, hybridization networks, and edge union networks. And all of these cases can result in a non-tree result. Now, cluster union networks takes all the clusters or groups of leaves. So you can think of them as taking subtrees, present in all the input trees, and then collect all the edges and branches together with the cluster subtrees. And then you have to filter out redundant edges that are placed in these. And that's actually a technique I'll mention later by Aho et al. Mia Miyagi and myself a couple of years ago proposed the edge union network that instead of focusing on the internal vertices, looked at the edges and the idea of collecting the edges from the input trees and putting them together. Again, also filtering out redundant edges and arcs. So how do we do this? Well, let's have some definitions here first. So we're talking about directed acyclic graphs, so rooted trees basically, and there can not unrooted splits and things like that. So we have a set of vertices and edges for each of these graphs. Now, the inputs don't have to be trees, they can be graphs or phylogenetic graphs. And there are 4 types of vertices. We can have a root with in degree equals 0, an out degree greater than 0, a leaf with an in degree or terminal with an in degree greater than 0, an out degree 0, a tree vertex with in degree equal 1 and out degree greater than 1, and a network vertex with in degree greater than 1 and out degree greater than 0. In general, so with these 4 types of vertices, we can create pretty much any graph we want in a phylogenetic analysis. In some cases, vertices with in degree 1 and out degree 1 can be created or present. They're usually contracted to remove them or basically ignored. Now, all edges are specified by a pair of vertices EU and are directed EDU, and there are no self edges, no loops or anything like that. The notion of phylogenetic networks of Moret et al. 2004, there can be further restrictions having to do with age consistency and things like that. I'm not going to talk about that here, but they can be further restrict the input set or the allowable set of input graphs. Now here we can look at different sorts of phylogenetic graphs. On the top left, we have a tree that we're all familiar with. In the center, we have networks where you see H211 has 2 parents. And you can have a multi-rooted network where you have multiple roots. And let's say these are different groups that have some sort of horizontal exchange, but we don't know how those 2 groups go together. And we can also have forests of these with multiple components that are networks, trees, or multi-rooted. So phylogenetic supergraphs. So what are we going to do here? We want to reconcile all of these diverse types of graphs, with different kinds of leaf complements, and put them together to get some sort of output graph that we can then use for various purposes. Now there are 2 basic approaches to this. One would be a vertex-based approach, and one would be an edge-based approach, or an HTU-based approach, or a branch approach. So on the left, you have the cluster union networks, which is is the original vertex-based approach, and then the edge-based approach of Miyagi and Wheeler on the right, which takes the edges. So those are the 2 basic kinds of reconciliation techniques I'm going to talk about. Now, there are common steps for all of these methods. And the first is we have to define a set of input forests. They could usually be input trees, but then in principle, they can be any kind of graph object, a directed graph object we're talking about. And then we have to collect all the leaves from all of these. So we have all the leaf sets. Now, each leaf in this entire input is assigned a unique label of a series of bits, basically a bit set, where it's on for that particular leaf, that its index, and off everywhere else. Each non-leaf vertex then of each component of each forest is assigned a bit label created as the union of its descendants. It's immediate descendants, but of course that would progress to the root of the tree. And so you, by a post-order traversal, and you create these bit representations, bit sets for all the nodes on the tree. And then of course the edges are labeled the same way. Vertices without degree 1 are labeled by prepending an on bit to the child vertex. And if you have, let's say you had 2 out degree 1 vertices that were connected to a single vertex, you would have a series of these 0, 1 sort of bits prepended to make sure that every vertex was uniquely labeled and that the subtree was always a subset of its parent vertex. Now, when we want to create the vertex-based approaches, we want to add a threshold to this. So we collect all the vertices present in a sufficient fraction of input graphs. So it might say, well, I want a majority rule. So it might be greater than 50%, or it might be some strict thing. So it's 100%, or I might say, I want everything. I want every possible vertex in there that's present in any of the input trees. And so in that case, the threshold could be 0. You create an initial edge set by creating an edge between each vertex and each other vertex whose bit label is a subset of that vertex. So that's what I mentioned before, is that basically every vertex bit labeling that is a subset of another one, there must be some sort of path between those two, a directed path. And so you create an edge between all these pairs, but you can identify and feed out a lot of the redundant edges from the initial set by using these bitwise comparisons. Basically, if something is if there's an intermediate bit set between two, you can remove that edge. And so the redundant edges are removed from this initial set. And this is a form of transitive closure that comes from Aho et al. 72 to reduce the edge set of the graph. Then we create the final edge set of the graph by subtracting the redundant edges from the initial set, and we have the edge set of our graph, which we then add to, of course, the vertex set, which we determine in the top set from threshold value, and then we have our resulting graph. Now, the edge-based threshold works in a similar way, but obviously focused on edges. So instead of a vertex threshold, we choose those edges that are present in some fraction of all the inputs, 0, majority, whatever you want, minority. It doesn't really, it's up to the user. And since the vertices are all uniquely labeled, that means all the edges are uniquely labeled as well. We also have to identify the redundant edges from this initial set, but it happens in a slightly different method by a breadth first search to look for things being spanned. But again, the redundant edges will be removed also in this case to get a minimal set. Then we have to create a vertex set via post-order traversal from the leaf set union of all vertices and at least one path P from leaves to roots. So basically we have to go to all the terminals, all the leaves. We have to do a post-order traversal to the root and make sure that, and get every vertex and every edge that is connected between some leaf and some root. We have to, because there could be isolated edges out there that play no role in the resulting graph. These are orphan edges, and we have to remove them. So then we create the final edge set by subtracting redundant edges and the orphan edges, and then we have our final set, and all the vertices that are connected in there up through the leaves are part of that graph as well. Now, to look at the complexity of these methods, like how much sort of time complexity we're looking at, we have an inputs forest set of size I, we have vertex set VI, unique edge set EI that come from all the inputs. And then, so these are sort of basic operations and their rough or overall time complexity. So the vertex bit labeling occurs by a single pass, a post-order pass of the graph, and that's pretty straightforward. So it's just the vertex size. If you want to counting the vertices to see if they are compatible or they're present in these different inputs, we have to compare them to each other. And so there's a factor for the size of the input, number of graphs, and then a square of the vertex set because they have to compare them. Then we have to create all these edges. That's also squared in the vertices. And then there's an additional factor multiplied by that for the redundant edge to check and see whether there are intermediate vertices that can be removed. So overall, you have a time complexity that is quadratic in the vertices, but with a factor for the size of the input set, and then cubic in the size of the vertex set that comes from the redundant edge filtering process. Now, when we look at the complexity set for the edge-based vectors, the edge-based techniques, we have the same forest set and the same unique vertex set, the same unique edge set. And we have some very similar operations. So we start with the vertex bit labeling. That is, of course, going to be linear with the number of vertices. And then we have to count the edges in the same way we counted vertices before. So that'll have to do with comparing all the edges to each other in all the input set. So that's going to be quadratic in the edges with a factor for the size of the number of input graphs. Then we have to create the vertices in post order. And then we have to, again, identify the redundant edges via breadth first search, which is a slightly different time complexity. It's squared, the quadratic in the edge set, and there's a product of the edge set and the vertex set in that. And then we have to collect all these and put them together via a traversal of the post-order traversal of the graph. So overall, we have something which is roughly quadratic in the edge set, but there's a factor of the input graph size, and then a factor of the product of the edge set and the vertex set. So these are different sorts of time complexities. There's no real cubic term here, which is nice. But overall, so you have very similar, you have elements that are similar and elements that are different in these two different forms of reconciliation. In the original paper we did, we showed that we actually have the sort of the polynomial time dependency on unique input edges that we anticipated, and this is our initial code. There's new code out there to do this sort of stuff today. And in that data set, we looked at a series of data sets, some which we'll look at today, having to do with spiders, walking sticks, metazoa, a number of simulated data sets, as well as some mitochondrial data sets and a linguistic data set of Uto-Aztecan languages in that particular case. So we want to look at how do these methods compare to existing methods. Well, if we look at the vertex-based thresholds, if we set threshold at 0, in the sense that we're going to take every vertex present in every input, that gets us the cluster union network. If we set the threshold at greater than 50% and the inputs are all trees, then we get the majority rule consensus tree. If we set the threshold at 100%, so any subtree has to be present in, or any vertex present in all the inputs, if the inputs are trees, we get a strict consensus. Of course, if the inputs are more general, we get objects that are not those. But this is how this method maps to some existing techniques. When we look at the edge-based thresholds, of course, it is a different kind of beast. But again, the threshold set at 0, take all the edges. That was how the initial edge union network was specified. Or we could do a majority rule or minority rule for that matter, or a strict edge force with only edges present in all the inputs. So one can do the same sort of manipulations here, setting threshold values. So as a simple example, we can take 4 input graphs here. You can see that 3 of them are trees. One of them is a network on D, the lower right, from HTU9. And then we can look at, this is a little bit busy, I apologize for that. But if we look at the different graphs here, let's look at, for instance, the upper right, C, that's a strict consensus, so to speak, of the input trees. Only those groups, in this case, C, D, that are present, all the inputs are present. We can do a majority rule in B, and you see we get an additional grouping here of EDC in addition to DC. And then if we look to A, we have the consensus union network basically with threshold of 0, which has a number of additional network edges. Now we can look at, let's see, below that we have some of the edge-based methods. So if we look at D, the lower right, we have the edge-based threshold where we take all the input edges, and that's the original edge union network. If we look at E, we have a majority of the edges. And you can see now we start getting forests because we've lost edges, we've lost connections to edges. So the edge-based methods, when you don't take all the input edges, you can have isolated components, like in this case, leaves A and B. And if we require that every edge be present in all inputs, in this case, we don't have any common information. And so we just have a series of isolated terminals showing there's no common leaf information. So you can see if you compare the upper right C to the lower left F, that the objects based on vertices and edges can be very different and give very different results. So I have some empirical examples here. We have Bantu linguistic data that came from Whiteley et al., about 105 languages, 92 words, a heteropteran data set, Weirach et al., morphology, multiple molecular loci, a metazoan data set of small ribosomal DNA, an Archean data set, also ribosomal DNA, about 585 taxa, and then a spider data set with about 1,000 taxa and about 10 loci, just for comparative purposes. And we can look at these, this very busy slide. You might focus on initially on the left, you can see that there are different varying numbers of input trees from low single digits to 100. Those were replicate data sets done as part of a search. The input leaves varying from 100 to 1,000 approximately. And then the input nodes, you can see varying from on the order of 400 to 8,000 for the Archean data set. And for these data sets that are relatively small, that have in the order of low hundreds of input leaves or single digits of trees, you can see these can be done in less than a second on a simple laptop. When you get to the larger data sets, you get into hundreds and thousands of seconds. The Archean data set especially would take tens of thousands, or 10 to 15,000 seconds for a large data set. But these are certainly, and these are sequential times. These are certainly manageable on sort of laptop common equipment. All the code is parallelized so that you can actually do things a little faster than that. Now, one might say the unfortunate aspect of things, here are a couple of examples. You can get a large number of edges in the outputs, and they look like these sort of spaghettigrams. And you can see from the CU and the heteropteran data set, you get a lot of edges, so you have to zoom in on things to see what you want to do or use automatic techniques. For the heteroptera, you can see for the EUN, you start getting a lot of isolated nodes. So there's not a lot of common edge information in these data sets. I'm going to skip through this for a second and just talk about, so here's the Bantu language data set, which has a minority rule reconciliation of 35%. The idea is those that are present in 1/3 of the input trees or input word trees can be shown. If we have a vertex-based analysis on the left, you can see we have a lot of common information at the base of the tree, and certain areas, sub areas of the leaves are robust, but on the edge-based data set, you can see that we have a lot of isolated components because there are not a lot of common edges. So the question is, so why would we want to do these sorts of things? Many of us use consensus techniques for all kinds of purposes, and one of which is we want to create a unified framework for graph reconciliation for all different types of input graphs. So if we have networks or forests or all sorts of things, we want to be able to put them together. And this technique here, or these techniques here, are general to phylogenetic graph types. So any kind of input graph can be used, directed graph that is, can be used to produce this directed output graph. And we can use this to serve as a summary of analysis, like existing consensus or super techniques. What's the common information among all these inputs, and what does that tell us about the data set? And we can also use these to start as the start of analysis in the sense of these alternate edges. These are candidates for hybrid origins or identification of horizontal gene transfer and sort of gene tree, species tree kind of analysis, or even lexical borrowing in linguistic data where words may come from different languages. English, for instance, has over 50% of its words come from other languages. So if you want to trace that sort of thing. So all this is on GitHub. So it's all open source. There are binaries is there as well from different platforms. And I want to thank very much the organizers for inviting me to this meeting, and then funding agencies, DARPA, the Kleberg Foundation, and the American Museum of Natural History, where I work, for my financial support. Thank you very much, and I'd be happy to answer any questions you might have in our existing time.
I am clapping because most of the audience can't. Hi, Ward.
Hey, Dennis, should I stop sharing my screen now or keep sharing my screen?
Oh, you may be sharing your screen, especially if you want to use your slides in case we have questions from the audience.
Okay,
a quick note to the audience, the next talk will be by Taran Grant, and that talk starts no matter what at 11:40, so 3 minutes from now. I will ask Gabriel to please put the link to that talk here. However, we can't keep here with questions and answers for a while because those are in different cyber spaces, let's say.
Okay.
Ward, I don't see any questions from the audience yet because they are still probably digesting everything that you said, but I do have a few that may help get things started.
Great.
Out of curiosity, are concepts like sister groups, like basic concepts, sister groups, synapomorphies, do they apply the same in this type of graphs?
Well, I mean, in terms of definition of sister groups being two taxa that are closest relative, have a shared parent that is the closest, that is unique to them, yes, they're there. What this would do, though, is say, okay, well, how consistent is that over all the graphs? Okay. Now, concepts of synapomorphy, that's a very interesting point. It goes back to the discussions we had about a long time ago, I guess now, maybe 20 years ago, about can you optimize characters on consensus trees? Remember, this was the discussion a while ago. And the answer really is, well, you can put them on there, but no, is the short answer, because the component trees have their own synapomorphy schemes, and the consensus trees are not meant to represent that, but the common areas of agreement among the inputs. Now, that being said, one would say if you have a very robust area of your consensus that's very well resolved and very consistently resolved, that if one had a synapomorphy scheme in there, it should be valid and useful. And that would apply to anywhere in the graph. But as a general statement, optimizing characters on this sort of object, you could do it, right? Because it could be a soft-wired network, let's say, or a hardwired network, or it might be a tree if you're lucky, or a polytomous tree. There are techniques to optimize characters on all of these kind of graph objects. So yes, one can definitely do that. The question is that what you want? Is that what you think it is? Is that what the object is that you're trying to consume? If one is saying that the actual character evolutionary pathways were this object with all kinds of stuff, then that will be appropriate. If you're just saying what's the common information, what's the different information among the outputs, it probably would not be.
So in that sense, how much different would be this type of information in informing taxonomic decisions once the analysis is completed?
Well, Taran's one, that's a good one to talk about this. The question is, when do you make a taxonomic change, right? Is it when you have information that the current taxonomy is not correct or does not reflect all the data? Or do you wait around until you get a lot of data to revise the taxonomy? And so I think that having an input network is going to be a problem for taxonomy in some sense, although there are ways to name hybrids and things like that. But I am no expert in this area, and I would really want to defer to someone like Taryn or some of your other speakers that have much more experience and knowledge in this than I do.
Fantastic. I do have a question before going to Vivian Amorim that has another question just in the audience. And my following question, well, let's go through hers. I think it's going to link very well. So Vivian Amorim says, do you think it's good using Supertree when have low resolution in tree?
Well, that's, I mean, in terms of identifying areas of agreement and disagreement, I think they're very useful. In terms of proofs and classification, I think it's not great, because it is not, in my mind, it's not really meant to be that. It's not meant to be a classification. And there, as we all know, there are lots of issues with super trees and how they're constructed. But I think most of those issues are legitimate criticisms for using them as classifications, so to speak, or using them as resultant trees. I don't think of them that way. So I don't think of them as being a problem, but I think for classifications, they absolutely are. That's not a good idea.
We are moving closer and closer, though we're not quite there, into having computers that are like quantum computers, and we are getting to computers that are usually faster. I wonder how far do you think we are from not worrying so much about the old notation of those algorithms?
Not far enough yet. Certainly parallelism helps, in existing sort of, Turing machines, we talk about them, but that's a linear factor, right? So you're not going to get some sort of factor of polymorphism of polynomial time. As far as things like quantum computing, in principle, we can do, NP-hard problems in linear time in principle, but there aren't really any around that we can buy yet. I think the real area for advancement is in algorithmic improvement. Can you make these things occur in lower time? For instance, the transitive closure aspect can be changed into a matrix multiplication problem. Then the best, I think, for matrix multiplication now is 2.376 or something, end of the 2.376, which is faster than the stuff that I'm doing here, if one were to do the exact optimal way to do that. So I think right now it's algorithmic improvements, maybe mathematical improvements that can do even better than algorithmic improvements to reimagine the problem in a different mathematical way. That will be our short to medium term improvements. But of course, if we all had quantum computers on our desk, that would be pretty nice too.
Awesome. I was fishing for that because that points out to us the direction that I would like students to know that there is room for improvement and so forth. I have a question by Yvonne Garzon. Again, I'm Brazilian. If I'm mispronouncing somebody's name, I'm sorry. And Yvonne Garzon says, why don't you use maximum likelihood or Bayesian inference that gives you just one tree? Wink.
Well, I mean, I'll take the wink. One would still have multiple trees potentially if you have multiple inputs, right? So if you have, let's say, a collection of phylogenomic data set and you have an analysis by whatever optimality criterion you want, Bayesian, maximum likelihood, at least Bayesian, let's say posterior probability, posterior probability sort of Bayes, like something like Beast does. You still have the issue of potentially reconciling the trees. Now, if you were going to look at the posterior probability of individual clades, well, that's what Mr. Bayes does with its majority rule consensus. So in that sense, it's useful for that technique. But given that for sampling reasons, not even necessarily biological reasons, but just from sampling, if you take different collections of characters and get different sets of trees, I think that's something that is a good thing to grapple with, as opposed to simply looking at one tree. Now, I'm not saying that consensus is better than, say, concatenation. I still think concatenation is superior. And if one were to do a maximum likelihood tree on a concatenated result, if it's identifiable, you'd get that single tree. And I think as a classification, that's superior to any combination of trees. But that's sort of I guess if I'm getting lost here, that's how I would differentiate those things. But the methods here are agnostic to the source tree creation. Like they could be fiat, they could be alphabetical order in English by common name, they could be maximum likelihood, Bayesian. These techniques are completely agnostic as to how the original trees were created.
Which is a good segue for my next question, which is, do you see these techniques as something that are going to be much easier for us to put together different types of information that perhaps we're not using so much right now?
Well, I hope that to be the case. And I'm working on some stuff now that would basically take these results and then use them as a starting point for actual sorts of searches or analysis of individual edges. And I think in that sense, these can be very useful for that sort, not just as a summary, but also as sort, you could think of them as initial heuristic solutions to problems that we face in phylogenetics.
Yeah, you, for example, have a lot of experience into even studying the evolution of languages or characteristics of languages, which is a particular very complicated type of data to work with. Would you say it would be easier to work with that type of data in this context?
I believe so. Certainly, you know, like I said, English is a horrible example of a pigeon, and that's one of the reasons why it's so difficult as well as so flexible. But certainly, if you look at Amerind languages in North America, there are a lot of Spanish and Portuguese words in there. Like anything, like the great example of that is for horse. Of course, there were no horses in North America until Europeans came over. So a lot of the words involved in technology of horses and agriculture based on horses are come from Spanish, or fruits and things like that that came from Europe. So the languages, that's a very interesting question, I think. It's, I think, analytically pretty much the same as looking at things like hybrid origins or horizontal gene transfer or things like that. But in languages, certainly we feel like we know that it's happening because we can see how different they are.
And one final question, I don't see other questions from the audience unless I'm mistaken. So currently I'm working a lot on viruses, specifically on the evolution of coronaviruses, and viruses are something that are under, one of the things that can happen is that they are under recombination. Available tools currently to study recombination are very flooded. They often only work with a few genomes at a time. Not even if the genome is very long, maybe only 4 or 5 genomes at a time. And it's very hard to distinguish between a recombination event from something that occurred due to, let's say, convergent evolution, because the methods are not very quite suited for you to measure the difference between the probability of recombination versus the probability of convergent evolution, for example. Would you say that using the summarization strategies and new graphs that you are proposing, could we leverage that somehow to identify putative recombination events in viruses?
Yes, and in fact, the data, one of the data sets I looked at first actually was influenza. And I know that your work with Dan Janney is one of the other speakers and things, you've actually studied a lot of these issues. And you know, the swine flu that ran through Mexico and about 12 years ago or so in the United States, that was an example, a putative example of recombination, right? Or reassortment of bacterial sort of elements. And I think, yeah, this is one of the rationales for allowing multi-rooted objects, because one can imagine you might have 2 different viruses and you really have no idea where they came from. But by a co-infection or something, some other mechanism, they come to exchange some information. And so I think that could be a good way to start studying some of those questions, or a good tool to use.
Well, Ward, thank you so much for being here with us today and honoring our tiny event with your presence. I would like to thank the audience and Gabriel for helping us out setting this up. He was one of the organizers of this event. Ward, do you have any final words before I close this?
Well, I just want to thank Dennis and everybody for inviting me. It's I wish I could see everyone, but that'll be impossible. And I look forward to seeing everybody at the next physical meeting, wherever it is and whenever it is. I can't wait to see everybody again. But thanks again and bye-bye.
Thank you very much. And I would like to ask our friends at UNC Charlotte Desk to close this session. Thank you again, Ward, and see you everybody soon.